Study the first kind of turbine, Pelton wheel turbine. This is an example of impulse turbine. R is generally the degree of reaction. This is 0 for a reaction turbine. Sorry, for a impulse turbine. The energy transfer is not because of change in pressure. So pressure is constant everywhere, which means these turbines can be without casing, open to atmosphere. The entire energy transfer is because of impulse. This is how a Pelton wheel looks. This is the wheel. This is the center. These are the buckets. There are multiple buckets like this. This is where water is stored. It is called head race. From the head race, the water comes through this called as penstock. This is the nozzle. The water hits the blade and the wheel rotates in this direction. The wheel, the buckets. These are the buckets. This is the wheel. The buckets looks something of this sort. This is known as splitter ridge. If we see the bucket from this cross section, the bucket would look something like this. Okay, this is the inlet velocity. This one at v1. This nozzle moves with the velocity of u. So this is u. This is w1. We can write only u, not u1. Okay, because this is a cross section and this r is same, omega is same, so u is same. So there is only u, not u1, u2. This is the exit velocity triangle. Okay, so this is sorry. W2 u is v2. So the Pelton wheel, we have this is the Euler equation, Euler energy per unit mass. This is v u2 v1 u1 minus v u2 u2. This is for a turbine where this the fluid enters with a higher energy and leaves with a lower energy, right? So U1 and U2 is same, so U into V U1 minus V U2. Since VU1 is in this direction, VU2 is in this direction, we can write this as plus. So this is equals to U into VU1 is the V. This entire thing is V plus VU2. This is VU2. This can be written as WU2. This is WU2 minus U. This is W1. Okay. This is the velocity of the fluid with respect to the blade. W1 comes from here, goes around and moves out from here, right? So W2 is equals to K into W1, where K is the friction factor, friction between the water and the blade. So we have and WU2 is equals to this beta W2 cos beta. Now this equation can be written as this thing. U into V plus W2 cos beta 2 minus U U to 1 plus W1 into K cos beta 2 minus U. This is V. W2 is changed by this. Now the efficiency this V, okay, this now this this V can be written as U plus W1 into K cos beta 2 minus U. Then this cancels out, so U into W1 1 plus K cos beta 2. W1 can again be written as V minus U to 1 plus K cos beta 2, right? Now this efficiency is U into V minus U 1 plus K cos beta 2 divided by the energy. The energy that is given by the inlet fluid is at a velocity of V1 is mv square. So V square by 2 because it is per unit mass. This we can write as U by V into 1 minus U by V into 1 plus K cos beta 2, right? To 2. So if you want to find the speed of the wheel, the relation between a speed of the wheel, speed of the bucket, and the speed at which the water leaves the nozzle, that is du by V This is equals to, this is a constant, multiplying these two, let's say a into 1 minus 2 u by v. So if we make this 0, we have u by v is equals to half. If you have again differentiate it, we will get it as minus 2a. So from maxima minima theorem, if d square efficiency by du by whole square is negative, then this is the maxima. And if we try to plot this graph, which is efficiency versus u by v, have a graph like this. But this is 1 and this is 0.5. The actual graph would look something like this. So this will be the maximum efficiency. This is theoretical, this is actual.